Dr. Evelina Curtis is a scientist turned entrepreneur with a PhD in neuroscience and with 20 plus peer-reviewed papers published to her name as well. After academia, she transitioned into business development and technology commercialization, advising tech companies on sales, partnerships, and market strategies. She speaks publicly on innovation, neuroscience, and the intersection of science and entrepreneurship. I am going to ask her to do a bit more of introduction to her work and what she's involved with at the moment. Before we do, I want to introduce to the audience that this is going to be the first of a whole series of conversations about the developments surrounding AI, various tech, developments and the convergence between sort of human and artificial intelligence, which of course is a huge debating point at the moment. If there's any particular speakers that the audience wants to hear on the channel, do please send through your suggestions as well as suggestions on topics which you think are important to cover as well. But for now, Evelina, welcome to the channel.
Hello, nice to meet you.
So, what did I miss out in your biography? What are your core focuses and what organizations are you working with in order to sort of make a difference in the field?
So I'm Evelina Curtis. I have PhD in neuroscience, and as you said, indeed, after some time, I moved to industry, to startups, to work with startups, and I currently work with Final Spark, which is a Swiss startup, which is building computers from living neurons. That means that we want to replace processor, which we have today, processors with processors built from living neurons, the same as we have in our heads today.
Is this a field that's relatively new, or is there quite a big sort of, let's say, hinterland of a couple of decades of research that are now coming into more of a sort of focus for commercialization, or is this a brand new field?
It's not totally new because, let's say, from maybe 30 years, there were some research in electrophysiology, which is about how different tissues may transduct electrical activity. But focus on computers, on building computers, was not so strong. We can say it's maybe last 10 years. Also because technology now it's make it possible because before such a research would be very difficult. Today we can have a huge amount, actually unlimited amounts of neurons, human neurons, which we can derive from human skin. This is a method for which there was a Nobel Prize around 15 years ago. And today we can have huge amounts of neurons very easily. And this is one of the reasons why such a research is possible. Because before it was quite difficult to get neurons. And they were usually from mice or rats and not in such a huge quantities.
Of course, a lot of the public focus, a lot of the debate, especially on platforms like YouTube, is focusing on developed around quantum computing, on AI. And actually, the big focus, of course, is on large language models. It's on how to handle data sets. It's on the software rather than the hardware, as it were. Um, how does the field that you're looking at, which is sort of more human-like neurons, how does that relate to both quantum computing and the sort of softer side of sort of modeling data that has given rise to a lot of the conversation, ChatGPT, and this quantum leap in possibilities?
So this is unconventional computing, so the same as quantum. This is the new way of computing where we have completely new hardware and also software. Everything will be totally different because if hardware is different, then everything else around this will be also totally new. So from our side is the main reason why we work on this is because current digital technologies are very energy consuming. They consume high quantities of energy and there is some limit to this. So we know that AI, the energy consumption of AI is increasing exponentially, and for today we still can manage, but we can expect that in few years it can be a problem. So this is why people are thinking about new ways of computing. So that's I would say also that biocomputing, so computing on living neurons, can be complementary to other technologies. So it's not like quantum and it's not like digital. It can be complementary and it can be suitable, particularly in our opinion, to the tasks which are today done by artificial neurons. We think that real neurons will be more efficient in this. And indeed, as you mentioned, LLMs, generative AI, we think also it will be great for generative AI because we can, by looking at the human brain, we can have an idea in which task neurons can be better, living neurons. So we expect that it could be good in the tasks which where speed is not crucial, but where energy consumption will be way lower as compared to digital, which we have today.
And of course, the introduction of LLMs produced certain things which I think very few people were expecting, and that was this extraordinary change in the, ability to process information and actually get sort of valuable insights with much larger data sets, and the stuff that people are now using with ChatGPT and it's starting to feel a lot more like sort of human response. Are there limitations on that? Are there limitations on hardware and the capability of large language models, given that you say there's a certain sort of energy barrier? Does that
Mhm.
also translate into a kind of analytical or understanding barrier that we're going to start bumping up against soon?
I think the main barrier could be energy consumption because today to build an LLM, you just need huge servers. So the people are also thinking about maybe alternative energy sources, which could be possible, maybe to make a stronger AI. So I think today the main problem is energy and also maybe quality of the data because LLMs already learned everything what is on the internet. And now the next question, which sometimes I see in some publications, is how to get high quality data so that LLMs don't learn stupid things. And actually, that's particular thing about computers that they need huge amount of data to learn. So this is why it's quite challenging to build. This is why also training them costs so much energy. But when we look at the human brain, and we can expect that neurons would need much less energy and much less data also, much less data to learn because we can learn the difference between dog and cat just by seeing one example, while computer needs huge amounts of examples. So we can have some ideas in which kind of things these biocomputers built from living neurons can be better. So for sure we can expect they will need less data.
Is there any difference as well in the sort of analytical processes that will be possible? So, um, there are certain methodologies in terms of how, large data sets are squished down to something intelligible. And as you ask more complex problems, especially complex sort of mathematical problems, the result doesn't necessarily improve through further cycles of analyzing these large models. Sometimes further computation can actually degrade the quality of results. Do you see new hardware as being able to provide new sort of analytical processes and capacities which aren't currently available, leading to, an exponential improvement in results as you go through that process, rather than, let's say, degradation of results?
We can expect this. We don't know yet fully how neurons process information. We know for sure that it's different than digital, and also they encode information in totally different way. So these are things which we know for sure, but we don't know exactly how it looks. Today we do experiments on biocomputers, so we are trying to test different approach on how to program them. But for sure they will process information differently, and that will be something totally different than today computer. So I think we cannot really compare the way how the data how is handled by a computer today and how the learning of language models or any other models. We cannot really compare this with what will happen with biocomputer. It will be something completely different. But I can also say that we don't really expect that biocomputers will completely replace digital. That's not what we really think. We think it will be complementary technology, and I think the future will look like there will be a lot of hybrid technologies. So there will be just a lot of new chips, not only digital, and they will be all connected somehow.
Is it possibly, and this is very much entering the sci-fi realm, is it more compatible with, let's say, human add-ons, as it were, or providing an interface between humans and current systems? Do you see a point at which humans become augmented using sort of biological neurons to improve, not necessarily to create entities that are more intelligent than ourselves, but to upscale human intelligence?
Yes, I think people are augmented all the time actually with technology. It's interesting topic. We were talking with many philosophers because we get a lot of questions, about our research. So we also talk with philosophers about of technology, and actually they also think that we are constantly augmented, and the technology, there is no really border between us and technology. Also with our smartphone, for example, it's something, it just changes us all the time. And we are not the same people as 20 years ago or 50 years ago when we used the maps, for example, on the paper, and today we use Google Maps. So I think technology is constantly changing us and is augmenting us. Absolutely. And today, a lot of cognitive function actually is switched to technology. And now there are some papers that we are becoming maybe slower or more stupid because we use a lot of LLMs. But I think it's just the trend in general. Like before, you had to count in your head after you had calculators, and everything is always changing. So maybe we will do different cognitive tasks in the future because more things will be replaced by technology. But I think it doesn't matter if it will be by a computer or digital. So this will always happen. I think so. This doesn't matter because actually this biological computer matters only, for actually for energy consumption, things like this. I don't think it will change the interaction with technology. Also because we maybe also expect that this biocomputer will be covered by a layer, of digital technology, which will help to interface. So, for example, it will be easier to program them because today is very difficult to work on neurons because you have to understand neuroscience, you have to understand the hardware. But as we have with computers today, there are many layers of abstraction. So today, when you program a computer digital, you don't have to really understand how the hardware is built. And the same may happen also for biocomputers, that in the future, when the technology will develop, there will be a lot of layers of abstraction. So at the end, our interface may be the same as with digital or quantum. They
And
may be
yeah.
different capabilities, but the interface can be the same.
And of course, that's the big debate in AI at the moment, isn't it? One of the first jobs, ironically, in previous levels of technological innovation and the Industrial Revolution, it replaced muscle and it replaced let's say, intelligent. Okay, a lot of crafts were mechanized,
Yes.
absolutely, but it replaced sort of muscle and brain. What we're seeing now is the replacement of brain, and of course, it is programmers themselves, ironically, who are in the forefront of potentially being put out of a job by AI as it writes code, and as we're entering an era where AI can self-improve code and iterate code. Would you see this sort of self-iteration improvement, or even the foundational code being written by the bioneurons themselves, and very rapidly overtaking what human capability can do in that area?
Yes, it's possible, absolutely. We expect that biocomputers will be able to do what today can do generative AI. But as I said, I think it doesn't matter if it will be biocomputer or digital. Uh, for sure, computers will be able to do a lot of our cognitive function, and this is reality. And it doesn't matter which technology will be used. Biocomputers will only use less energy. That will be the difference. But I think we have to prepare for the fact, which is already happening, that AI is replacing a lot of tasks. And what I personally believe that there will be new jobs, maybe new things happening. Like today we have, for example, search engine optimization manager is a job which didn't exist 20 years ago when we didn't have internet. So I would expect maybe with new technologies, a lot of things current jobs will be eliminated, but there will be maybe some future jobs which we cannot imagine today.
You've hit the nail on the head there because that's my profession, and I'm moving into podcasts because I see that as something which is far more human-led, and actually AIs will be able to do podcasting, but I think people will always want to listen to humans discussing these topics.
True.
So, it's a slightly safer area than search engine optimization, which I see going the way of the dinosaurs relatively soon. Um, Talking of energy efficiency, I'm absolutely fascinated by obviously the possibilities of quantum computing, but at the moment, of course, in hardware systems, you need to chill them down to extraordinarily low temperatures in order to preserve sort of the quantum state, and they're rather unstable and very, very difficult to manage. Is it possible that science is starting to show that biological systems can achieve for certain discrete functions quantum states in biological systems, which we hadn't previously thought possible, at a far lower energy consumption and without having to go down to, extraordinary low temperatures for things like photosynthesis and so on? It's becoming apparent that there are, quantum processes at work there. Do you see an advantage of biological computing that we can actually make more advances with far lower energy consumption in the quantum computing race as well?
No, to be honest, I don't know anything about quantum computing. And I know maybe there are some hypotheses related to neuroscience, but they are very niche, I would say. So I don't know. I think that quantum computers are suitable for other things, maybe for cryptography, which is definitely not a good case for biocomputers because it would require very fast, very quick calculation. And characteristic of biological tissue is not the speed. Actually, neurons are very slow. So we rather would expect they would solve totally different problems than quantum. And about the energy, it's funny because actually neurons, they don't need low energy. They actually need 36 degrees Celsius, like in our bodies. So they need a physiological temperature is much easier, I would say, maybe than getting this critical, very low temperatures in quantum.
And of course, that needs to be maintained rather than sort of overheating, as it were. Um, that's a fascinating idea that actually neurons are relatively slow at certain tasks and capable of others. So, what kind of tasks would they ideally be applied to, especially if you envisage not a pure sort of biological computing world, but a sort of a hybrid approach there? How does it complement traditional computing, and what kind of tasks does it lend itself to?
We could expect by looking at human brain that generative AI could be a good task because human can generate ideas, can generate context, content, and many things with a very, very low energy consumption. So we could expect this, for example.
And
Although it's really hard to say today
it,
because,
yeah.
we do very basic research at the moment. And at the moment, we were able to store one bit of information in our neurons. So this is why everything about the task is really a speculation. We can guess something based on looking at the brain, but we don't know yet for sure what will be the capabilities of biocomputers.
So, what's the timeline for developing this further? And is there a critical threshold of the number of neurons which would be required to start delivering, practical results, and where, let's say, traditional manufacturers of chips and so on will sit up and start paying attention?
It's a very good question. So this is long-term project. We expect it will take around 10 years to build bioservers. So will be huge biocomputers which will be available remotely. As today is our lab actually also can be accessed remotely, but for research. And currently our biggest challenge is learning in vitro. So how to change connections between neurons because this is how they learn, how to make them perform some specific behavior in terms of activity, for example, electrical activity. So these are like the beginnings of programming of neurons. And we expect it will take another 2 or 3 years. It also depends on investment because we are currently self-funded by the founders, and we are searching for 50 million of dollars of investment. And this, of course, can accelerate our development. So we expect that with investment, we can reach in vitro learning within 2, 3 years. And later, the next step will be advanced learning. So we have to be able to perform tasks which will be at the same quality as digital computers. And the third milestone will be scaling. So we want to make huge structures of tissue because at the moment we have very little. For experiments, it's enough. We have around 10,000 neurons. These are such a circle structures, such a little blobs of cells, which we put on electrodes. And this is okay for experiments. But in the future, when it works, when we would like to make huge structure of neurons, and then build central bioservers, which will be available remotely. And then we expect to make money since 2033. And then we think that it will explode. If it works, then we will have a very competitive processing power for processing information. Very competitive compared to the digital technologies.
And I can hear people in the audience asking maybe ethical questions. Is there a critical threshold where people might say, "Well, hang on a second, you've got a volume of neurons here that could be compared to the volume in a living creature, whether it be a bird or, something larger than that. And also, could there be emergent properties which are unpredictable when you reach a certain kind of critical threshold of neurons?"
Actually, we want to build structures which will be much bigger than any brain known today, because we want to build structures of even 100 meters long with the neurons. So it will be something really huge. And yes, we get questions a lot about consciousness of these neurons. And this is why, actually, because we are scientists, we are engineers, we are not really experts in philosophy. So this is why we reach out to philosophers to propose them this topic for research. And actually, there will be study in the UK in the group of researchers, I think from Nottingham, if I remember good, who will do a study about public perception and other philosophical questions related to biocomputing. Because indeed, there is a lot of discussion about this, but it's the same also for digital, because there is a lot of discussion whether LLMs are thinking or not. Recently, there were very famous paper circulating that it's illusion of thinking in LLMs, but there were also a response that
That's the Apple paper,
it's
wasn't
illusion
it?
of the
Yeah,
illusion.
yeah.
Yes, so this is really difficult because it's funny. Actually, consciousness is something we cannot measure, and we cannot be sure actually even about consciousness of other people. We know only our own consciousness. So there is no measure. It's all based on speculation. So actually, it's very difficult topic because you cannot prove anything. This is also a line of reasoning, but everyone can build a different line of reasoning. So this is why we think philosophers are best for this kind of questions. Also because we really want that this technology which we're building will be acceptable by society. So of course we want to do our best that that all the ethical problems are solved. So we know how to work with this and what we should do to make it for the benefit, of course, of the society.
And let's face it, some humans do a fairly passable job of creating an illusion of thinking, especially politicians. Um, It's absolutely fascinating there. Do we know enough about the brain, actually, about how it encodes information, how it accesses information, the prioritization it makes when it's needing to do some kind of analytical work? Do we know enough about the actual functioning of the brain? Or is that also a key part of your research at the same time as trying to sort of build these, neuron systems?
No, we don't know enough, absolutely. And this is why our laboratory is fully automated. So we built such a system where we can have huge amount of experiments because we actually have to use trial and error method in trying to program neurons because nobody really knows how they encode information and how they process this information at the very basic level. This is also a huge question, since maybe 30, 50, 30 years at least in research, because there is such a field like neuromorphic computing, where people try to build digital or analog hardware, which is inspired by the brain. So they don't use really living neurons, but they try to play with the different materials. And this field is still ongoing. There is still a lot of progress in this, and people also try to mimic the brain, but nobody really knows how brain encodes information. So usually you have to hard code. You have to say, okay, this signal would mean this, another signal something else, but we cannot really follow the natural uh, properties of the brain, how it encodes information. So it's ongoing problem, and that's also great that we can work on real living neurons, because maybe we will be able to solve this puzzle. And I think this will be a huge, huge progress, not only for biocomputing, because if we know how brain is processing information, then we have huge opportunity to cure maybe some neurodegenerative diseases. There is a lot of interest in this, or how to improve human brain. Maybe one day we can learn a new language by just programming it. Of course, these are science fiction ideas, but I think this kind of research which we do about how neurons process signals, this kind of research can contribute to this, also to the new techniques on how to interact or how to change a human brain.
We'll get onto these sort of ethical and regulatory concerns in a minute, but is one of the fundamental issues that you're trying to tackle here the idea of whether AI can produce genuine originality, and or is it simply a large language model can only be a sum of its parts? It can never be more than a sum of the parts. Is that one of the key challenges, or are we seeing, emergent ideas which we didn't have before, or is it simply spotting patterns in data which we hadn't spotted? And will these biological systems be able to crack that problem of producing genuine originality?
This will be hard to say. We can say that humans can produce original content, original things. So we could expect maybe neurons in vitro also, but it's pure speculation. It's hard to say. But based on looking at the brain, we can expect this will be possible.
Well, let's get on to the regulatory framework then, because I th I think governments, whether it's ethical concerns or regulatory concerns, really struggle to keep up with the current pace of development. And we also see that in actually, concerns around the media. And the fact that over many decades, in fact, over a couple of hundred years, we've built frameworks around how to deal with print media and information in the print medium since, the printing press was invented. That didn't, happen overnight. It happened over a long period of time. But we had that. Now presented with the digital information, it's as if we've forgotten all that stuff and we struggle to build any regulatory framework to handle sort of the flood of sort of digital and social media information. Do you have concerns that in this era of biological computing, that really our systems of governance and lawmaking are just not built for the task of being able to sort of regulate at the pace that the technology is developing?
Yes, I think regulators have a hard time because everything is going very fast, but it's general tendency. Also in scientific research, you can see that there is huge, huge amount of papers published today, which is exceeding far, far what was done before the speed in this speed. So I think it's a general problem, and but I think it's a normal thing, and we just have to accept the fact that there will be new technologies coming, and maybe regulations will come later. I think it's just inevitable. And also, in some cases, it's really difficult maybe to prepare some legislation before technology exists, because we just don't know how it works. And I think it's very dangerous to write a law about things we don't understand. This is actually can cause a lot of problems and a lot of costs, and will make us much slower also and less competitive as compared to other countries. So I think it's a big problem, and I think the law should be written very carefully. and with the understanding. So it can be normal that they always need some time to catch up. I think it's fine.
Let's turn to the topic of learning, because I think one of the challenges of large language models and indeed sort of processing through ChatGPT and so on is, of course, yes, it's massively energy hungry to produce an answer. It crunches vast amounts of data. But where it really struggles is to then have a memory of the answer it's given and a memory of the data that's been processed. So if you ask another query, you're often starting again from scratch, and without any, let's say, sort of positive feedback on the answer was given or memory. Do you see far more efficient learning processes happening through a potentially, I don't know if you call it wetware, but through
Yes, wetware
biological
is
systems.
absolutely the right word. Yes.
Okay.
Wetware
Um,
computing is also, yeah, there are many words, because it's a new field. So sometimes you can find different terminology. So yes, absolutely. We would expect much more efficient learning because as I mentioned before, we can learn the difference between dog and cat by one example only. And for a computer, it's needed much more. And also every interaction for a living tissue, for neurons, is changing them because actually neurons are a dynamic system in contrary to the digital. So that means they change all the time, and the same as our brains, they change also through the interaction. So actually, yes, I would say the interaction might also affect the structure and of the tissue, and maybe the memory will be better. Because actually, what is also funny is that in neurons, memory and processing information is happening in the same place. So that's also the difference between digital and neurons. So yes, I think it will be maybe easier than with the LLMs.
where it may be harder, though, of course, is to then understand what the processing is, what's happened. So you get a particular result, and it's already incredibly difficult to kind of reverse engineer and to understand how, the large language model came to a particular conclusion. And you'd have to sift through huge amounts of data to sort of reverse engineer how that particular answer was come up with. Is that problem actually exponentially more difficult in wetware? So you may get better answers, but we may find it far more difficult to reverse engineer or understand how those answers were derived.
Yes, absolutely. I think it will be more difficult because for now, living neurons are real black box because we cannot look inside the system. We cannot access weights individual like we can in digital neural networks. So yes, definitely, it can be black box, at least for today and at least for us. And it's generally difficult to look inside because the neural tissue is very complex. It has a lot of connections, and it's difficult to look inside. So it could be it could be that it will be a black box.
Yes, well, that's an interesting challenge, especially if it eventually comes to exceed human intelligence. That's going to be a tricky one. Are these systems potentially more resilient as well? Because we know that if for instance there was a massive solar flare, as there was in the 19th century, where the early telegraph systems around the world were fried, and that's suitably distant that we don't think too much about it. But of course, the current systems based on silicon are incredibly, I would say, vulnerable to large electromagnetic pulses. Is wetware far more resistant and resilient to those kind of shocks? Is it potentially more resilient to, let's say, uses in space, for instance, where you may have, high energy particles and so on?
This is a great question. Actually, I don't know. I'm not a physicist, so I don't know. But there are some research about using neurons in the space, but they are mainly done, I think, to check how neurons react on the particular circumstances in the space. So it's more for neuroscience. I don't know actually if they will be more resilient because actually human tissue, human neurons are very fragile. So they have. This is why we want to build central servers which will be accessible remotely. We don't think it's a good idea to sell biocomputers as a device which you can take home because of this, because neurons need a very, very special condition. And also in our heads, they are very, very fragile. So to be honest, I don't know. I think every technology is a bit fragile. So you always need some specific condition.
So you don't necessarily see these biological computers as being embedded in cars, watches, wearable materials, and so on. You see them far more being these sort of, server farms with particular, very curated conditions.
Yes, I absolutely think it makes much more sense. Although our competitors from Australia, Cortical Labs, they have built a first computer, which is something you can order to get at home. But yes, we definitely believe more in bioserver. Also because it will give you opportunity to make huge structures of neurons. So it can increase the capabilities of such a server much, much more.
And where's the ideal environment? Because, of course, at the moment, server farms require a lot of electricity. And as we move forward, ideally, that would be places with strong renewable resources,
Mhm.
as opposed to sort of fossil fuel resources. I mean, that doesn't always happen, because some of the conditions for server farms,
Mhm.
dry, arid, etc. places are not necessarily the best for the electricity production or necessarily cited where the electricity is produced. Where do you see it geographically as the optimal place for these server farms? And do you think it's important that green energy is one of those sources that powers them?
Well, I think it doesn't matter where in the world. Theoretically, it could be everywhere. Because I think having bioserver is quite feasible. You just need a lab, in vitro laboratory where you can grow neurons. So I think it can be done everywhere. And actually, it's done everywhere because you have universities and labs everywhere on the world. And I think, well, I don't know which kind of energy will be connected to these bioservers in 10 years. Maybe will be different than today for sure. But I think it will be huge, huge advantage anyway because these servers we have calculated because neurons are 1 million time more energy efficient than digital technologies. And even taking into account all the laboratory and all everything around what is needed to use them, we calculated that they will be still 10 times more energy efficient. So in any case, they will use much less energy than for example, digital technologies.
So in fact, they could be cited in many places because they don't actually require such a big energy input. Um, what would be, the most sort of resilient and scalable approach? Is it to have, a few large data centers or a much more distributed network? And when we think at the moment, in particular, military thinking says that actually, having a few large generators is an existential risk to your resilience. Whereas having a distributed network of nodes that can pick up the capacity
Mhm.
if some are taken out, do you foresee that same sort of approach here?
I think it's a bit too early to think about this because we are still on the R&D phase. So I think when we build the servers, we can consider also other options, like why there should be more of them than less. So I think it's too early a bit to think.
Well, let's turn then to more immediate and practical matters. So this is the sort of last sort of line of questioning here, but what is in your development timeline? What are you looking to achieve over the next couple of years? And what kind of partners, whether it's industry partners or research partners, are you really looking for to help move this technology forward and to find applications to which it could be applied?
So for the next 3 years, our biggest challenge is learning in vitro. So this means that we want to be able to change the connections between neurons and make them learn something in vitro in a dish. So that's the challenge for the partners where we have clients already, which is surprising. It's unexpected because our laboratory is available remotely. So actually anyone in the world can connect and can try interact with neurons in vitro. And initially we had collaboration with the universities, and after we have seen that there is also interest in industry. So we started to have industry clients who are paying us to use our laboratory remotely. So that's something we hope will develop. And of course, we are also talking to investors because we think it could be important to accelerate this work which we are doing with the investment. We think it's really a very good, well, we believe it's a good opportunity because when the bioservice will work, they will have a huge impact on the current AI industry, and they will be very profitable because it will be very competitive source of processing power as compared to the digital.
And, slightly sort of techie question there. So you see a strong future moving away from what's been called a von Neumann architecture.
Mhm.
That is that abstraction between code and data. And as you say in the brain, it brings those two things together in a way that traditional computing doesn't.
Well, for sure, I would see that there will be hybrid technologies, in my opinion. There will be different technologies, different, not only digital, not only what we know today, but there will be also quantum computing, there will be biocomputing, there will be a lot of different methods because different computing technologies are suitable for different tasks. So I think because our demand for processing power is increasing, then we will have more and more hardware which will be optimized for some specific tasks. That's what I believe. And for sure, they will be somehow connected in a hybrid system so that it all can work together.
Well, it's been absolutely fascinating, and I'd be keen to sort of keep an eye on what you're doing and the developments there, especially as you say, you're moving faster perhaps than you expected, and you have customers ahead of what would normally be, expected at a very early developmental cycle, which is absolutely fascinating. We'll put links into the description if people want to find out more, where they can, get in touch with you and your team, and also learn more about the topics we've discussed. For today, though, it's been absolutely fascinating exploring this sort of cutting edge area of computing science. Thank you, Evelina.
Thank you so much.